Hello everyone, I am Hazur Ahmed and I am from Information Technology University. Today I am going to present SuperSlash, a unified design space exploration and model compression methodology for the design of deep learning accelerators. This is an outcome of my PhD work and it is in collaboration with the Vienna University of Technology and New York University of Abu Dhabi. Here is the outline of this presentation and I will start with the introduction. Over the past decade, deep neural networks have achieved remarkable success by providing a state-of-the-art accuracy in several challenging computer vision tasks such as image classification, image captioning, semantic segmentation, object recognition, and autonomous driving. This slide is showing you image classification error for some of the prominent deep learning architectures. It can be observed that, in general, for ImageNet, as shown here, most of the recent networks require more operations as compared to the previous ones in order to have better accuracy. But this results in larger networks having large storage and compute requirements. Therefore, DNNs in practice are compute intensive and memory expensive, and their processing requires millions of parameters and billions of operations. On this slide, we will discuss pipeline of DNN flow and acceleration. There are three main stages of DNN acceleration: model creation using popular libraries such as TensorFlow, Caffe, Keras, etc. Training on related datasets. For the inference, we have many choices depending upon the availability and conditions of our application. There is growing interest towards carrying out the inference on the resource constrained edge devices. Such devices have a limited on-chip memory, and that's why the operations are carried out on a small subset of input data which we call the tiles. And for the same reason, these operations are to be carried out on the small tiles of the input feature maps, output feature maps, and weights. Provided a DNN model, here we are particularly considering custom hardware accelerators which allow you to customize the design according to the requirements. Design space exploration is thus carried out to explore multiple tile configurations and data reuse strategies such as input reuse oriented, output reuse oriented, and weight reuse oriented. Model compression via pruning and design space exploration have been mostly carried out independently in the past by the previous work. However, there is a caveat because model compression might not be tuned for particular design constraint. Here we demonstrate that why we believe that we should consider multiple design options while pruning the network. Here we demonstrate three pruned models M1, M2 and M3. M1 is achieved after applying the layer-wise pruning ratio as reported by Lee. M2 is obtained by using our proposed technique, and M3 is generated by equally distributing the pruning budget across all the layers. In this figure, we plot off-chip access volume obtained by performing design space exploration over input reuse oriented, output reuse oriented, and weight reuse oriented reuse strategies with global buffer size of 32 KB. Thus, there are two key insights. Even for the same model, different reuse strategies result in different off-chip access volume. And even for the same reuse strategy, three pruned models require different off-chip access volume. We also demonstrate that pruning the same number of parameters from different layers results in different off-chip access volume. To show this, we compared off-chip access volume of VG16 model after removing 2.5, 5 and 7.5% parameters from the layer 6 and layer 13 and obtained 6 pruned models. Pruning the same amount of parameters from layer 6 provides greater benefits in terms of reduced off-chip access memory. We have observed that even with the same amount of parameters removed from the different layers can result in different off-chip access volume. Consequently, provided a pruning ratio goal, distribution of the pruning budget across the network layers while aiming low off-chip access volume is a challenging task. Since different pruning techniques may remove different number of parameters from the network layers, even for the same cumulative pruning ratio, we evaluate if DSE carried out for one model is indeed applicable to another. Here we provide the design space explored for two models, M1 which was lease model and M2 which was the model obtained from our proposed methodology. Here we show the off-chip access volume for a hardware accelerator considering multiple on-chip memory sizes, while varying the global buffer size from 32 KB to 512 KB. And here we show that the best design for M1 is not necessarily the best design for M2. If the DSE is carried with respect to lease model, this is the best off-chip access that can we get. However, if the same design parameters are utilized for any other pruning technique, we get performance degradation. However, if the design space exploration was carried out with respect to M2 itself, we can get better design point. That's why it is important to consider design consideration while pruning the model. Our motivational analysis demonstrates that a key challenge is to devise a unified methodology which performs co-exploration of our DNN model and its associated design space while minimizing the off-chip memory access volume. Now let's see what novel contributions do we have. In this paper, we present SuperSlash, a unified co-exploration methodology that employs a layer-wise ranking function to rank the pruning suitability of each layer by considering its off-chip memory access volume overhead that is estimated via an in-tandem DSE. In particular, the DSE evaluates multiple data reuse strategies for each layer and associated tile sizes and the possibility to apply layer fusion across any two consecutive layers. Provided an accuracy constraint, it distributes the available pruning budget across multiple layers of a DNN model by incorporating the proposed ranking function for predefined on-chip buffer size. Now we come to the SuperSlash methodology. SuperSlash methodology supports the generic architectural topology of various on-chip deep learning accelerators. Such accelerators typically comprise of an on-chip global buffer to share the tiles of input feature map, output feature maps, and weights, and a neural processing array which can comprise of multiple processing elements. Neural processing array fetches the data from global buffer and applies the convolutional pooling and activation operations and stores the result back in the global buffer. The control unit is typically responsible for fetching the input feature maps, output feature maps, and weight tiles from the off-chip memory in a scheduled manner as directed by the chosen data reuse strategy. Design space exploration is thus carried out to select a layer-wise data reuse strategy and the corresponding tile sizes for the input feature maps, output feature maps, and weights. Our SuperSlash methodology performs this DSE along with a model compression scheme that is aimed at reducing the off-chip access volume. Provided a DNN model, the available on-chip buffer size, and a minimum accuracy constraint, our methodology minimizes the off-chip access volume via pruning the model. The SuperSlash methodology comprises of 4 steps and is illustrated in this figure. In step 1, the SuperSlash takes as an input the original model along with the provided constraints. Design space exploration has been performed for minimum off-chip access volume. In this step, DSE is performed taking single layer processing and multi-layer processing into consideration. SuperSlash looks for the possibility of layer fusion by keeping the output feature map tiles of the first layer and using it as the input feature map tile of the next layer. In step 2a, a rank is assigned to each layer based on its off-chip access volume. In step 2b, layer-wise ranking is employed to prune the layers in a progressive manner. We repeat step 1 and step 2 iteratively until accuracy threshold is evaluated. If at any point the accuracy of the pruned model falls below the accuracy threshold, a fine-tuning step is performed to regain the lost accuracy. Thus, step 1 to 3 define one SuperSlash iteration, where step 3 runs only if the accuracy constraint is violated. In case the network cannot be compressed further within the accuracy constraints, the last known acceptable model is passed over to the step 4 for fine-tuning and final DSE. SuperSlash allows using the pruning ratio and off-chip memory access level as the terminating condition. In this case, a relaxed accuracy constraint can be provided and the iterations are terminated with desired pruning ratio or off-chip memory access level is reached. In the first step of our methodology, SuperSlash performs design space exploration and off-chip memory access computation. For a DSE model, W of I with L number of layers being provided as an input to the ith iteration of SuperSlash, the model is completely defined by the number of filters or output feature map channels, number of input feature map channels, number of rows of output feature map, number of columns of output feature map, kernel size, stride, and pulled-in filter size. For a batch of D inputs, the layer-wise data volume required to accumulate all the input feature maps, output feature maps, and weights can be computed using these relations. Since global buffer size is limited, only tiles can be brought in the on-chip memory. Therefore, the total memory in the global buffer to stored in one instance of each of these tiles is given in this equation. Using the layer-wise data volume and tile size parameters, we can compute the off-chip memory access factor, the number of times a tile of data is required to be shuttled for each of the input feature map, output feature map, and weight. These access factors depend upon the data reuse strategy being employed and are given by the following relations. Note that the access factors for input feature maps, output feature maps, and weights are 1 for IRO, ORO, and WRO respectively, since for each of these cases the tiles are required to be shuttled only once. For a particular data reuse strategy, the total layer-wise off-chip access volume is equal to the sum of the products of the corresponding data volumes and access factors and is given by these equations. The above equations are valid for single layer processing. SuperSlash also investigates the possibility of layer fusion by utilizing the output feature map tile of the Lth layer as an input feature map of the L plus 1th layer, and the equations of the multi-layer processing are given in these relations. Since our DSE is very large, we employ some strategies to reduce it. First, we make use of reuse factors to choose among the data reuse strategies. Reuse factors for input feature maps and output feature maps and weights are defined as follows. If the data reuse factor for weights is large, we select WRO as data reuse strategy and search through the search ranges indicated in the following table. We select data reuse strategies of the other in a similar way. This algorithm summarizes the procedure of solving DSE for a given model. For further details, kindly go to the relevant sections in the paper. In step 2 of our methodology, SuperSlash assigns a rank to each of the layers of the network. The ranking function is thus defined as follows. Model exploration of a given model at the ith cycle is given by the following algorithm. For further details, you can also refer to the relevant sections in the paper. Now we shall be discussing the results. This table shows the layer-wise comparison of Lee's model on Smart Shuttle DSE with SuperSlash. Here is a given model configuration. This particular filter configuration represents our model, and this is the design configuration of output model of SuperSlash. Unlike Lee, we don't only provide the pruned model as an output, but we also provide the design configurations tuned for particular model. Moreover, Lee's model seems to be handcrafted, while our model is automatically generated from the Unified Collaboration Framework. Since Lee's paper itself does not provide the design configurations, for the sake of comparison, we selected Smart Shuttle, which is our DSE technique to explore its tile sizes. However, Smart Shuttle does not consider layer fusion, which we also consider. It can be observed that SuperSlash obtains substantial reduction in off-chip access volume as compared to the state of the art. For further insights in this figure, we plot the layer-wise off-chip access volume as bar plots on the left y-axis and pruning ratios as line plots on the right y-axis. It can be observed that SuperSlash applied a greater pruning ratio to the layers that have higher off-chip access volume. For example, layer 9 and 10 have the highest off-chip access volume. Therefore, SuperSlash tries to remove more parameters in these layers, whereas Lee applies same pruning ratio to all the layers from the layer 9 to layer 13. Similarly, layer 6 and layer 7, Lee does not prune these layers at all. On the other hand, our model is pruning each layer as guided by their off-chip access volume. Therefore, SuperSlash prunes the layers in proportion to the off-chip memory access volume. In this figure, we evaluated the global buffer size impact on the off-chip access volume. We performed our design space exploration for various values of global buffer sizes varying from 32 KB to 512 KB and report the total off-chip access volume on this diagram. We observe that our SuperSlash provides greater gains for the more challenging design configurations when the global buffer size is small. This is because for the smaller global buffer size, more data is required to be shuttled, and hence there is relatively greater benefit of off-chip aware pruning. We also evaluated the design points explored by SuperSlash. This figure illustrates that we have very large design space. Particularly, unlike the other DSE, we have one extra dimension related to pruning ratio. For each prune model, we have multiple design points. And it can be observed for the SuperSlash model. The SuperSlash DSE is getting better results as compared to the Smart Shuttle DSE, and its performance is close to the exhaustive search. This is due to the extended design space traversed by SuperSlash owing to its better strategies for the search space reduction. Hence, our evaluations demonstrate that SuperSlash provides an extended design space by incorporating the accuracy dimensions in the DSE. This is achieved by adding the pruning ratio in our unified exploration, unified design space, and model compression via pruning methodology provide us with the design points that have lower off-chip memory access volume as compared with the state of the art without any manual intervention. We performed a detailed comparison with multiple state-of-the-art pruning techniques called popular networks. This table provides the accuracy, achieved parameters remaining, and the flops remaining after the application of pruning. For all networks, SuperSlash achieves the comparable accuracy with the same pruning ratio and obtains substantial drop in the off-chip memory access volume. For VGE16, we achieved up to 57.7% reduction in the off-chip memory access volume as compared to the state of the art. Similarly, for ResNet 56, ResNet 110, and MobileNet V1, we achieve 25.8, 47.7, and 29% reduction in the off-chip access volume as compared to the state of the art, respectively. Thus, we demonstrate that the SuperSlash provides comparable accuracy for several popular DNN and as compared to the state of the art, and our technique provides design points that require low off-chip memory access volume as compared to the state of the art, thus demonstrating the robustness of the methodology. We now summarize our paper. We have devised a unified methodology for model compression and design space exploration. Provided a DNN model, we iteratively prune the layers based on layer-wise off-chip memory access volume estimate. This allows the pruning to be steered towards design points that require low off-chip memory access volume. We have achieved 64% reduction in VGA16 model size and saved 49% off-chip memory access volume. Similarly, we pruned ResNet 56, ResNet 110, and MobileNet V1 on CIFAR 10 and achieved a significant reduction in memory access volume. And finally, to facilitate further research and reproducibility of the presented results, we have provided a public release of our pruned networks and framework at the following link. So, here is it for now. For further inquiries, you can refer to the paper, and for any queries, you are more than welcome.